My daughter's. So in the first example, it just says simplify the following and state any restrictions on the variables. So you don't have to worry about that part. But to simplify these, and then I'll go through what the restrictions are just so you know. But to simplify that, the first thing you would do is there's nothing to simplify here except you see x squared minus 1. And x squared minus 1 is a difference of squares. So you would write that as x plus 1, x minus 1, because it's a difference of squares. So you can factor that by taking the square root of x squared and the square root of 1. So x plus 1, x minus 1. Once you've done that, the x plus 1s will cancel out on the top and the bottom, and the x minus 5s will cancel out. So that leaves you with absolutely nothing on the top of the fraction. So anytime you have nothing on top, you have to put a 1 there, and that leaves you with x minus 1 on the bottom. When it says state the restrictions, it basically means go to the beginning of the problem. So there's your answer, 1 over x minus 1. The state the restrictions means go to the beginning of the problem, and what numbers would make the bottom 0, basically, the denominator 0. So if it makes the denominator 0, obviously you can't divide by 0. So that means these are not possible. So a restriction would be 5, because 5 minus 5 would make it 0. A restriction would be 1. 1 squared minus 1 would make it 0. Negative 1. Negative 1 squared minus 1 would be 0. So those are your restrictions, 5, 1, and negative 1. So basically, a restriction is just something that can't happen. So you cannot have a denominator of 0. So you look at the beginning of the problem, and you say, what would create a denominator of 0? All right? So in B, we needed to factor both of these, so we needed to say what two numbers multiply to give me negative 12 and add to give me a positive 1. So we have x squared plus x minus 12. So they're going to multiply to give me negative 12 and add to give me positive 1. That's an x plus 4 and an x minus 3. So x plus 4 and x minus 3, that's on top. On the bottom, I say what two numbers multiply to give me 12 and add to give me 7. So that's an x plus 4 and an x plus 3. So you have x plus 4 and x minus 3 on top. You have x plus 4 and x plus 3 on the bottom. So the x plus 4s will cancel out. That gives you x minus 3 over x plus 3 is your final answer. Now, to figure out what would make these 0, you look at it when it's factored. If x plus 4, a negative 4 would make it 0. You can't divide by a negative 4. And a negative 3 would make it 0. So negative 4 and negative 3 are called your restrictions, because if you plug those in for x, make the denominator 0, and you can't divide by 0. So that's just example number 1. All right, so let's go into the next thing is the vocabulary you need to know. First thing is called a vertical asymptote. Okay, a vertical asymptote is where the denominator of a function equals 0. So basically exactly what I was just telling you about. If the denominator, where the denominator of a function equals 0, that is called a vertical asymptote. And you're going to see that on the graph. What it looks like is it's basically reaching a point, but it stops at that point. And the next thing is called a point of discontinuity. So discontinuity means it's discontinuous, which means it stops. And that would be what we would call a hole in the graph. Okay, so basically instead of the graph just continuing on, it stops at a certain point. And then it says there's a star over there to the left. You see it says x-intercepts are any quantities that are left in the numerator. So your x-intercept is where it crosses, obviously, the x-axis. That is anything that's left in the numerator. So, for example, if x minus 3 is left in the numerator, you know you're going to have an x-intercept at 3 because that was left in the top of the fraction. In the first problem, you don't have an x-intercept because there's nothing left in the numerator because everything canceled out. But if for some reason there's something left, like right here, there's x minus 3 left in the numerator, then that means you will have an x-intercept there at 3. Okay, so let's look at example 2. It says determine the equations of any vertical asymptotes and the values of x for any holes in the graph. So the first thing you have to do for this example is to factor it. That's the goal of the whole unit, is to make sure you can factor it first. This is a difference of squares. So we have x minus 1, x plus 1 on top. On the bottom, you say what two numbers multiply to give me positive 5 and add to give me.
Yeah, you're correct.
Yeah, that is wrong.
Yeah.
Why'd they do that? So it should be negative 5x plus 6. Okay, what two numbers multiply to give me positive 6 and add to give me a negative 5? So that's x minus 2 and x minus 3. So that was written wrong on the paper. All right, so in that case, I have x minus 1 and x plus 1 on top, and I have x minus 2 and x minus 3 on the bottom. So nothing cancels out. Okay, so holes in the graph, and we'll talk about where that's at. There are none in this one, and we'll talk about why there would be one in a graph. Vertical asymptotes are where the denominator of a function equals 0. So vertical asymptotes are these down here. That would be 2 and 3. If you set these equal to 0, x minus 2 equals 0, you would get 2. And x minus 3 equals 0, you would get 3. So 2 and 3 are your vertical asymptotes. And then your x-intercepts are, remember, any quantities that are left in the numerator. So x minus 1 and x plus 1. So 1 and negative 1 are your x-intercepts. That's where it crosses the x-axis. It crosses at 1 and at negative 1. And I'm going to let you see what the graph looks like.
But if the x-intercept, would it be written 1 on the 0? And that's where the x is. The x-intercept.
I believe so. I think that's wrong too. That's two incorrect things on there. All right, if you'll look, here is what the graph looks like. These graphs look very strange, okay? All right, so here's what the graph looks like. An important thing to note is there's your two x-intercepts. That's where it crosses the x-axis, okay? This right here, if you'll follow it, you see it goes to, you can follow it up, but see this one, it looks like the x is approaching the number 2, and this one, it looks like the x is approaching the number 3. Those are called your vertical asymptotes. That means as far up as we go, we can go all the way up to infinity here. It'll never get to 3. It just gets closer. The x gets closer and closer to 3, and the x gets closer and closer to 2. So it makes the graph look kind of strange because they're just going up like that. But those are your those are your vertical asymptotes. Vertical means going up. And so it'll be at where x equals 2, so it's getting closer to 2. And then this one's getting closer and closer to 3. So you have vertical asymptotes at 2 and 3. That's what those are in the graph. So you can actually see what it looks like. The negative 1 and the positive 1, you can see that on the x-intercept. Okay, so let's go to the second one. Example 3. Determine the equations of any vertical asymptotes and the values of x for any holes in the graph. So in this case, x squared minus 4 is a difference of squares. So that's x plus 2 and x minus 2. So that's the top. And then on the bottom, you're saying what two numbers multiply to give me 6 and add to give me 5. That's x plus 2 and x plus 3. So in this one, we actually had something cancel out. When something cancels out, it creates a hole in the graph. So that's how you know if there's a hole or not. So in example 2, there was not a hole in the graph because nothing canceled out. In example 3, there is a hole in the graph because the x plus 2's cancel out. So where they cancel out, it creates a hole at x equals negative 2. So you basically just set equal to 0. So x equals negative 2 is a hole in the graph, and we'll talk about that. The vertical asymptote, remember, is If you forget that, you can look on your notes. It's where the denominator equals 0. So there's only an x plus 3 left. So it's when x is negative 3. That would be a vertical asymptote. And the x-intercept is going to be at 2, 0. Okay? So it's going to cross the x-axis at 2 because that's what's left in the numerator. And so now we can look at this one if you want to. It'd be the same as the other one. So we can check out this graph. So it's x squared minus 4 over x squared plus 5x plus 6. So notice, you can see where it crosses at 2. Notice the vertical asymptote we talked about. This going up, notice how it's going towards negative 3, the x, but it doesn't get to negative 3. Notice going down, how it's going towards negative 3, but it will never get to negative 3, but that's where it's headed. So you can see that negative 3, if you zoom in, is where it's getting closer and closer to. So that is your vertical asymptote. Okay? You also, in this problem, if we go back, you have an x-intercept of 2, 0. We have a hole at x equals negative 2. So when x is negative 2, look, notice, see that right there? Right there. It says undefined. That means it's a hole. That means it cannot equal negative 2. And that's because that it canceled out there. So if you look at it on the graph, you actually are able to, if you go over it with your mouse, you can see that there is a hole there on the graph. That means it's not defined at negative 2. And that's because we canceled those out. All right? So those are just some common things that you notice. These are, rational graphs are really weird, like looking. They're strange from the ones you're normally used to, but that'll help you go through it. All right, let's look at these last 3. These are the big 3 things that we need to look at. So on these 3 questions, let's look at the first one. The first one says x plus 4 over x squared plus 5x plus 4. So on the bottom, you need to factor. You have 2 numbers that multiply to give me 4 and add to give me 5. That's x plus 4 and x plus 1. So the x plus 4s cancel out. That immediately lets me fill in the hole at x equals negative 4. So I immediately know, because the x plus 4s cancel out, that I have a hole at x equals negative 4. Okay? I have x plus 1 left in the denominator. So that immediately tells me I have a vertical asymptote at x equals negative 1. Okay? Because that number's left in the denominator. Now, x-intercepts is what's left in the numerator. There was nothing left in the numerator, so I have no x-intercepts. There's none. So that top line is all the things we've done so far. The vertical asymptotes, the holes, and the x-intercepts. Now, if it says, so here's how you know about the horizontal asymptote. Horizontal means as it's going left and right, where is it going to? Okay? It says if m is less than n. So this is m stands for the degree of the numerator, n stands for the degree of the denominator. If the numerator has a smaller degree than the denominator, which this one does, numerator goes to the first degree, the denominator goes to the second degree, then you automatically know that it has a horizontal asymptote at y equals 0. So that means it goes straight to 0. And we'll see that in just a minute. So that's the first step. The only reason we knew this right here, was because this degree is less than this degree. Okay? Now notice, the domain goes from negative infinity to negative 4, then it picks up at negative 4 to negative 1, then it goes from negative 1 to infinity. So anywhere there's a vertical asymptote or a hole, that causes, and I know this can be difficult, but that causes a break in the graph. So think about the graph. The graph is going from negative infinity to positive infinity. But anywhere you have a vertical asymptote, which is like where it never reaches that point, or a hole, that causes a break in the graph. So just think, I'm going from negative infinity to positive infinity. But on my way from negative infinity to positive infinity, there's a hole at -4. So I have to stop at -4. Okay? Then I pick back up at -4, but then there's a vertical asymptote at -1. So I have to stop at -1. And then I pick back up at -1 and I go all the way to infinity. Okay? That's what the domain is saying. So anytime there's a hole or a vertical asymptote, you stop. You're always going from -infinity to +infinity. But anytime there's a hole or a vertical asymptote, you stop. So let's look at we can look quickly at what the graph looks like. It is x plus 4 over x squared plus 5x plus 4. So it looks like this. You see there's no x-intercept, so it never crossed the x-axis, even though it gets close to it. So there's no x-intercept. You see there's a hole. It says that x equals -4. If you don't believe me, you can find it. There it is right there. So there's your hole. It says there's a vertical asymptote at x equals -1. That means this one's getting closer and closer to -1. You see the x, it's at -0.9, and it's going up. And then over here, it's at -1. It's getting closer and closer to -1. So you can see that vertical asymptote is at -1. And then notice it said the horizontal asymptote was 0. That's because the y, look how it's getting closer and closer to 0 as you go across the horizon. That's what you're seeing there. So the y is getting closer and closer to 0. All right, so that's the first one. Let's go to the second one. Second one says x squared plus 5x plus 4. We already factored that in the first one. So we know that's x plus 4 and x plus 1. And then on the bottom, we have 4x squared minus 9. That's a difference of squares. So the square root of 4x squared is 2x. Square root of 9 is 3. So we say 2x plus 3, 2x minus 3. So nothing cancels out in that one. Now, nothing cancels out. So that means we have vertical asymptotes where the denominator equals 0. So if you say 2x minus 3 equals 0 and you solve that, you get 3/2. If you say 2x plus 3 equals 0, then you solve that for x, you get -3/2. So that's where the vertical asymptotes come from. They set these equal to 0. Holes, where we cancel things out, there's none because we didn't cancel anything out in this second problem. X-intercepts, that's where the top would be 0. So x plus 4, so there's one at -4. X plus 1, so there's one at -1. So there's an x-intercept at -4 and at -1. Means it crosses the x-axis there. Okay? Horizontal asymptote. Now, we learned in the first problem, if this degree is less than this degree, it's 0. But what if this degree is the same as this degree? They both go to the second power. So if they're equal degrees, it says the horizontal asymptote is the fraction of the leading coefficients. So the numbers in front, basically. So what's the number in front of x squared? 1. And what's the number in front of x squared here? 4. So 1/4. It's that simple. You look in front of your first number and say, what numbers are they? They're 1/4. Now, remember, your domain always goes from -infinity to +infinity, and it stops where there's a hole or a vertical asymptote. There are no holes here, so it's only going to stop where there's a vertical asymptote. So we go from -infinity all the way to -3/2, and we have to stop. Then we pick back up at -3/2 and go to 3/2, then we have to stop, and then we go from 3/2 all the way to infinity. So we're just going from -infinity to +infinity, and we're just stopping where there's a hole or a vertical asymptote. And on Desmos, you look at the graph. The graph will just kind of confirm your results too. And there it is. you see it crosses at -4 and -1. So that's where it crosses the x-axis. You see a vertical asymptote. You can see where this number is going to. It's going to 1.5, 1.5. See how it's getting closer and closer to 1.5, the x. And down here, the same. Okay. You also can see there is one over here on the other side at -1.5. So it's getting closer and closer to -1.5. That's your other vertical asymptote. Then your horizontal asymptote, this means the y is getting closer and closer to 1/4. So notice 1/4 would be 0.25, right? See how it's getting closer to 0.25? And over here, it would be getting closer to 0.25. Further you go. That's how you get the 1/4. So these can be difficult to read, but they do reflect your answers on there. So last one. If the top degree is higher than the bottom, there is no horizontal asymptote. Okay? So right in the beginning, if this degree is higher than this degree, there is none. If this one is less than this degree, then we know it's 0. And if it's higher than the degree, we know there's none.
Where's that one? That's what we read.
Yeah, it might have flipped you to the second page. Sorry. Okay, so if m is greater than n, so if the top of the fraction has a higher degree than the bottom of the fraction, then there is no horizontal asymptote. Now, the vertical asymptote comes from, so we did x squared plus 5x plus 4. 4 and 1 add to give you 5 and multiply to give you 4. So the x plus 4 is canceled out. So that means everything in the denominator canceled out. So that's why there's no vertical asymptote, because there's nothing in the denominator. So it canceled out. There's nothing in the bottom of the fraction, so there's no vertical asymptote. There is a hole, however, at -4 because you canceled out at x plus 4. So when you cancel out at x plus 4, that creates the hole at -4. There is an x-intercept at -1 because you have x plus 1 left in the numerator in the top of the fraction. And remember, the domain is going from -infinity to +infinity. It has to stop at a vertical asymptote or a hole. There is a hole at -4, so it goes from -infinity to -4. Then it picks back up at -4 and goes to infinity. So the final answer, that one actually looked a little bit simpler, but if there's a larger degree in the numerator, there is no horizontal asymptote. So we learned that by looking at this. So we go to the last graph. Again, x squared plus 5x plus 4 over x plus 4. When that cancels out, guess what? You end up with x plus 1. So anybody know what that graph looks like? It's a line. It's linear, right? Because when everything canceled out, it's just x plus 1. So you got an x-intercept at -1. You do have a hole in the graph at -4. Those are not easy to see. You have to look. There it is. You have a hole at -4. But other than that, it goes from -infinity to +infinity, right? So that's why our domain goes from -infinity to -4 and -4 to infinity. Okay. So remember, vertical asymptotes are when it's going up and down. You can get those by what is left in the denominator. So what's left in the denominator tells you what your vertical asymptotes are. Your holes come from what canceled out. Your x-intercepts come from what's left in the numerator. Your horizontal asymptotes come from what's the degree of the top and the bottom. Your domain always goes from -infinity to +infinity and stops where there's a vertical asymptote or where there is a hole. So that is graphing rationals. That's a lot, and I know it can be confusing when you look at vertical and horizontal asymptotes, but you're going to get those again in your next math class. So this is kind of the introduction to that, and that way you can see the graphs. If it was for the exam, you would be able to use Desmos to graph it. You would be able to look at what cancels out. The key in rationals in this unit, Unit 7, is if you can't factor, you can't do it. So you've got to really be very good with your factoring and make sure that you understand how to do the factoring. They're usually basic factoring, where it's either a difference of squares or two things that multiply to give me this and add to give me this, but you've got to be able to factor. So that's a key part here.